Hello and welcome to this month's webinar from CWNP on Advanced Radio Frequency for Wireless Pros. My name is Tom Carpenter. I'm the CTO at CWNP. And as always, you can find us on Twitter at CWNP and at CarpenterTom if you'd like to follow us on Twitter to get announcements about upcoming webinars and other events. I would like to begin by reminding you that the Wireless Technology Forum 2020 is well underway with bookings, and we are excited about the speaker lineup we have this year and the pre-conference training. Of course, we'll have our CWNA track courses there, CWNA, CWSP, CWAP, CWDP, and we'll also have the available CWISE or ISA tracks. So these are the new certifications focused on IoT. Originally branded as CWSA, we're referring to it now as CWISA, and we also have two new certifications in that track this year. One, the Connectivity Professional, and the other, the Integration Professional. The Connectivity Professional is focused on understanding IoT protocols in depth, and the Integration Professional is focused on understanding how to integrate these different IoT systems and particularly the data that they generate together. So very exciting certifications, and both of those courses will be running at the conference this year as well. So to find out more information, of course, you can always go to the website and learn about the conference, when it will take place, and how you can get registered. Okay, with that said, let's take a look at what we're going to be covering this month. So first of all, we're going to talk about radio frequency defined and compared. Now this is called Advanced RF for Wireless Pros, and what that really means is we're going to go a little bit under the hood. We're going to get underneath of what happens and what takes place in electrical systems that allows radio frequency to occur. So we'll talk about radio frequency itself and compare some of the different frequency bands briefly. Then we're going to go under the hood, talk about electricity in RF, RF transmission, and then come back to the different frequency bands and understand the impact of what we've learned on the different bands. So with that, radio frequency defined. We can define radio frequency as the combination of electric and magnetic fields in a section of the electromagnetic spectrum ranging from a few kilohertz to roughly 300 gigahertz. And it's used for analog and digital communications, among other things. So this is the range that we might think about for actual communications, depending on what kind of communications are taking place. The primary characteristics of a radio frequency wave are, of course, the frequency, it's in the name, the amplitude, and the wavelength. Now, the actual difference between these is important to understand, and the impact that it's going to have on your resulting system. So the frequency is the cycles per second. How many times does the wave repeat per second? So if you imagine a point in space and the wave traveling past that point in space, how many times does a full wave travel past that point in space per second? That's the frequency. The amplitude is the strength of the wave, and we measure that in watts, milliwatts, or dBm. So we often measure it in watts or milliwatts at the output power side, but we rarely think of it in watts or milliwatts at the receive side of the link. There, we're thinking of it in dBm because dBm can represent very low power levels with numbers we can wrap our minds around. For example, minus 63 dBm is a very low power level. It doesn't sound like it. It sounds like just minus 63, but it's a very low power level if we were to look at it in milliwatts. So therefore, we use dBm on the receive side. Now you'll also see dBm on the output side. It depends on the interface that the vendor uses for the wireless device, whether they choose to have the output power of the wireless device be listed in milliwatts or even watts or in dBm. So it will vary there, but on the receive side, we generally just think about it in dBm. Now, you will also see on the receive side, some systems just tell you you have a good signal or a poor signal. Well, one of the reasons for that, particularly in the world of IoT, the reality is that a lot of signals can definitely be received as long as they're above some threshold. So as long as they're above that threshold, the receiver will simply report it's a good signal. And if it's below that threshold, it will say it's a poor signal or a bad signal. And that is because they have one modulation rate and only one modulation rate, and nothing varies. So if you're used to Wi-Fi, you're used to varied data rates or modulation rates. And because of that, you're used to realizing that if you have a weaker signal to a certain point, you just keep getting a lower and lower data rate until, of course, eventually it is so weak that the signal is gone. And whether we call it good or bad or great or excellent depends on what you're using it for. If I only have a 1 megabit per second connection on Wi-Fi and that's all I need, then it's a good connection. It's good for my need. But if I need a 150 megabits per second connection, then 1 megabit is not good. So that's the key, is understanding that when you see some of those IoT systems that just tell you you've got a good signal or a bad signal, in some cases that's because they just need a signal good enough to get the only data rate they support through. And as long as they have that, it's a good signal. That's not to say that the signal couldn't have been measured in dBm, but it doesn't necessarily have to be illustrated to you in that way. We can demodulate, we have low error rates, and so everything is good. So that's the amplitude of the wave. And then the wavelength is how long the wave is, literally physically how long it is, measured in meters, centimeters, millimeters. Now we can't see these waves with our physical eyes. And we really can't even see these waves with measuring instruments per se. We don't really see the wave traveling through the air. Even if we pick it up with an antenna and we look at it inside of a spectrum analyzer, you probably notice you're seeing amplitude strengths of the signal. You're not really seeing the wave form per se when you're looking at that. And that's because it would be wildly complicated to regenerate and display that waveform for you so you could see it. So we can't really see them, but we know they have a particular length. And this all comes from the mathematical theory behind radio frequency, or electromagnetic waves more specifically. And that is that electromagnetic waves travel at the speed of light. And since they travel at the speed of light, we can know that to move from point A to point B based on the speed at which they travel, they must have a particular wavelength given the frequency. Or if you knew the wavelength, you could say they must have a particular frequency given the wavelength. And so frequency and wavelength are interrelated based on the constant, which is the speed of light. Now let's have a visual representation of this wavelength factor and frequency. So I find one of the best ways to grasp it is to look at a fixed time window and see how many waves we can fit into that time window. So what I've done is I've chosen a time window that fits one 400 megahertz wave into that window. We see that in the upper left. Then we see one 800 megahertz wave. We see that in the upper middle. Then we see one 2400 megahertz or 2.4 gigahertz wave. Then a 5200 megahertz or 5.2 gigahertz wave. Then a 6000 megahertz or 6 gigahertz wave. And finally, a 24 gigahertz wave. And so you can see the different number of waves that are crammed into that same time window in order to accommodate that frequency. And so it's important to understand that the higher the frequency, the shorter the wavelength, and the lower the frequency, the longer the wavelength. Higher frequency, shorter wavelength, lower frequency, longer wavelength. Now, IoT technologies tend to use 400, 800, and 2400 megahertz. Some of them are playing around in 3.5 gigahertz and using CBRS for IoT type things, but that's not by far the most heavily used for IoT specifically. And some will even use 5 and 6 gigahertz and even 60 gigahertz. So you could do an IoT device using, for example, 802.11 DMG, directed multi-gigabit PHY. So you could actually use 60 gigahertz if you wanted to and do IoT. You can. 6 gigahertz has just been opened up, so we could see 802.11ax IoT devices using the 6 gigahertz band, right? 5 gigahertz is already there with Wi-Fi, and it's there with some other technologies as well that might be classified as an IoT device. So there are some that might use those, but the vast majority of IoT protocol communications that are not cellular-based IoT are using 400, 800, 900, and 2400 megahertz. And that's really why I kind of chose those three at the top. I didn't also represent 900 megahertz here because it's pretty close to 800, not a significant difference that you would see. But we do see the difference between 400 and 800 and then 800 and 2400 and 2400 and 5200. And what you can see is they're roughly doubling the number of waves each time between 400 and 800, and then tripling between 800 and 2400, and then almost doubling between 2400 and 5200, which makes sense, right? Because we're doubling or tripling the frequency. So it makes sense that you would see that many more. So we have 4 times as many waves fitting into the same time span with 24 gigahertz as we do in 6,000 or 6 gigahertz, 6,000 megahertz or 6 gigahertz. So that gives you a comparison of the different frequencies rather than just me telling you that indeed the wavelength differs with higher and lower frequencies. Now, the next thing I want to do is I want to move on and talk a little bit about electricity. We could talk about electricity for a very, very long time. We could spend 8 to 10 hours just having a basic course on electricity, certainly. But I want to give you some fundamentals because it helps you kind of understand how things work. And these fundamentals apply to wired networking, where we use basically electrical currents to transmit signals. And we do it in RF when we send the radio frequency signal down the wire or the connector on the way to the antenna. And as that moves through the antenna, what happens there? So we're going to talk a little bit about that. Now, electric current, if we want to think of it as current, the flow of electricity, happens through a conductor in the fact that that conductor is made up of atoms, right? And atoms have a nucleus, wherein we have protons and neutrons, and we also have electrons. Now, some electrons in an atom are what are sometimes called bound electrons, meaning that they don't really get away from the nucleus. They're so attracted to the nucleus that they can't escape. But then there are other electrons that are what you might call in the outer orbit of the nucleus that we call free electrons because they can escape, they can get away from the atom, right? So the flow of current is the flow of electrons from atom to atom through the material. This is what we theorize as to what's taking place here. So it's important to know that what we're dealing with here is the move of electrons from one atom to another through this material. So everything starts with the atom. And it includes an understanding of electricity and therefore electromagnetic waves. Atoms, as I said, have protons, electrons, and neutrons. Now, protons have a positive charge, and electrons have a negative charge. Neutrons are neutral. They're neither negative nor positive. The nucleus of the atom contains the protons and neutrons, and we see them here represented in green and gray. The electrons orbit around the nucleus in the outer shell or outer region of the atom. Now, in some materials, as I said, the electrons are bound electrons. They're tightly bound to the nucleus. They can't easily move from one atom to the other. And these materials are called insulators. Other materials allow the electrons, those free electrons or mobile electrons, to move from one atom to another. These materials are called conductors. So the wire inside of an RF cable is a conductor. The shielding around the cable, it's an insulator. This design allows the electrons to flow along the cable and very few escaping in comparison to those traveling along the cable. Now, this concept of moving electrons is the foundation of electricity and electric theory and electromagnetic theory. While electromagnetic waves don't contain atoms, they're theorized in quantum theory to be comprised of photons, it's the behavior of atoms in the antenna that results in the radiation of electromagnetic waves. In the same way, it's the behavior of atoms in the antenna in response to incoming electromagnetic waves that allows for reception. The theory states that an atom absorbs energy, and this causes electrons to move within the atom. When the electrons return to their original position, an electromagnetic wave is produced. We'll see this more when we talk about antennas later, but stated differently, when the electron is accelerated or decelerated, there's a change in that movement, it produces an electromagnetic wave. So effectively, electric current travels to the antenna, and the antenna releases the electromagnetic waves on transmission. When electromagnetic waves strike an antenna on reception, the result is a generated electric current that's transferred from the antenna to the radio on reception. This electric current is the RF signal traveling through the wires or connectors to and from the antenna. Now, when a material has an excess of electrons, it's said to be negatively charged. When it has a lack of electrons, it says to be positively charged. And I know that sounds odd. We refer to the electrons. We say there are more electrons than protons, for example, then it's negatively charged. When it has fewer electrons than protons, it's positively charged. But there's another way you can think of it. If you have fewer protons than electrons, it's negatively charged. And if you have more protons than electrons, it's positively charged. Now the negative and positive terms make sense. So we always talk about the electrons, but it's just a way to think about it to make the positive and the negative make sense. When a material has the same number of electrons and protons, it's said to be neutrally charged, or simply neutral. And the same can be stated at the atomic level. An atom with more electrons than protons is negatively charged, and an atom with fewer electrons than protons is positively charged. So this gives you some idea. Free electrons are said to flow. They give you current from one atom to the next atom, taking their charge with them as they travel. To theorize a bit about this, the concept is that once that electron breaks free, it looks for something to attach to, and it's attracted to a nucleus, right? So it's attracted to the nucleus in the next atom, and then it breaks free from that atom, or another electron breaks free, and it's attracted to the next atom. And so there's this breaking free due to induced charge, and then the attraction to the next, which it causes an induced charge, which causes a breaking free, and well, you get the picture. All of this, of course, happens extremely fast, much faster than I can talk about it. Now, let's talk a little bit about electric units. First of all, it is important to remember that we have two types of current, alternating current and direct current. Understanding electric units and transmission methods is important for understanding the powering of devices in an IoT network, if for nothing else. So when you want to power your device in an IoT network or a wireless network, you're going to provide current to that device. Now, some of these same units or metrics come into play when considering transmission power in an RF system as well, like watts, for example. So first, electricity may be transmitted as alternating current, AC, or direct current, DC. And no, we're not talking about an old rock band. AC transmits the flow of charge and changes direction periodically. So it changes direction. It's therefore an alternating current. When the direction changes, the voltage level also changes with the current. Now, most power delivered to offices and homes is AC power. So what's coming to your home is AC. An automobile uses an alternator to generate AC power for the components in the vehicle. The current from the alternators typically pass through a diode, which converts it from AC to DC for use by the vehicle's battery. Now, DC provides a constant flow for a constant voltage. Batteries provide DC power, and AC power can be converted to DC power with rectifiers, diodes, and other types of components. An AC adapter takes the non-constant power from the mains power supply and provides a constant DC flow for a device that requires it, like a laptop, a wireless access point, a Zigbee gateway, etc. For example, the AC adapter may allow a range of inputs, such as 100 to 250 volts, but provide a specific output, such as 12 volts DC at 500 milliamps. Okay, let's talk about volts and amps. A volt is named after Alexandre Volta, and the difference in electrical potential between 2 points of a conductor is really what the volt is. Specifically, when 1 ampere, or 1 amp, passes 1 watt of power between these 2 points, the difference is the volt. Voltage is measured in volts, and 1 volt is equal to 1 ampere times the resistance of 1 ohm. Bringing in a lot of terms here, aren't we? Let's keep defining. An ampere, or amp for short, is equal to the flow of 1 coulomb per second. Another term, a coulomb. It's the rate at which electrons move through a conductor. A coulomb is approximately 6.124 times 10 to the 18th power elementary charges. Fancy phrase for electrons. So a coulomb is approximately 6.124, or rather 6.241, times 10 to the 18th power elementary charges, or electrons. So 1 amp is 6.24 times 10 to the 18th power charges flowing by per second, or electrons flowing by per second. When an AC adapter is rated for output in milliamps, MA, such as 500 milliamps, it is measured in 1/1000th of an amp. So 500 milliamps is 1/2 of an amp, or it would be 3.12 times 10 to the 18th power charges flowing by per second. So amps measure the flow rate of the current, and volts measure the power of the current. This is similar to pressure on a water pipe. That's the voltage. And the flow rate of water. That's the amperage. The joule is the energy required to move the coulombs between 2 points. When a single joule of energy is to move 1 coulomb of charge between 2 points, the voltage is 1 volt. So when we talk about a volt, we're saying 1 volt is a single joule of energy being used to move 1 coulomb. Coulombs are used as a reference to avoid really large numbers because we've talked about that. So instead of saying 6 quintillion, 241 quadrillion, 509 trillion, 75 billion, 500 million elementary charges, we say 1 coulomb. Aren't you glad we say 1 coulomb? This is similar to measuring a bushel of grain instead of a kernel of grain, right? We don't want to pick out each kernel, so we take the whole bushel, and that's what we measure. The next metric is ohms, or the measure of resistance in the conducting medium. You can think of it kind of like the size of a water pipe. So when we say 1 volt is equal to 1 amp times the resistance of 1 ohm, all three are included, right? We've got now a volt, an amp, and an ohm. Materials with more free electrons have less resistance, and materials with fewer free electrons have more resistance. So conductors have many free electrons, and insulators have few free electrons. Now, Ohm's law states that current, or amps, flowing in a system changes in the same direction that the voltage changes, and in the opposite direction that the resistance changes. For example, current increases in a system when voltage increases, and resistance stays the same. Also, current decreases in a system when resistance increases and voltage stays the same. So it's very important to understand that. All right, so all of this, then what is a watt? Well, 1 watt is 1 joule per second. Therefore, 2 watts would be 2 joules per second. So a watt is a measure of energy produced or consumed in time. A milliwatt is 1/1000th of a watt, therefore 100 milliwatts is 0.1 joules per second. Okay, now I would encourage you, spend some time researching that in more information if you desire. I've given you the brief nutshell overview of that, but you might want to dig a little deeper into that to understand it. It's really intriguing, the theory of electric propagation through conductors. Now, the next thing we want to talk about then is what then is an electromagnetic wave? Well, an electric field coupled with a magnetic field is propagated through space as an electromagnetic wave. Electric fields are generated from electric charges and from changing magnetic fields. Interesting, a changing electric field can also generate a magnetic field. Therefore, E generates B and B generates E, which theorizes the method of self-propagation in electromagnetic waves. Now, it is important to note that polarization is based on the E field. So however the E field is positioned, that is your polarization. So if we say we have vertical polarization, then that means the E field is as we see depicted here. If we had horizontal polarization, then the E field would be as the B field is represented here. Okay, so what does this mean to antennas and everything we've talked about? Well, here's the cool thing. So you've got your RF cable connected to your radio, which is connected to your antenna. All these electrons move down the RF cable from the radiating antenna at a particular frequency, and then they move up and down the antenna at a particular frequency. And these moving electrons through the antenna cause the generation of an electromagnetic wave. So as they change within the antenna, they generate the electromagnetic wave. Remember that a changing electric field generates a magnetic field, and a changing magnetic field generates an electric field. So as these move up and down the antenna, they are resulting in this change. So here we see our electrons moving up and down the antenna, and the result is the generation of an electromagnetic wave. So that gives you a little bit of the underlying theory behind what takes place with our elements. There's more details. We could go into a whole lot more detail, but you know I like to keep these webinars somewhere around 30 to 35 or 40 minutes. And so we'll say that's good enough for now, but I've given you what you need as a starting point. If you want to go deeper into any of these, I encourage you to do so. Research electrons and electricity and electric flow. Study into this information, and I think you'll find a lot of moments of enlightenment. I call them light bulb moments. You know, the light bulb goes off, I really understand it, that kind of thing. Now, let's talk a little bit about signal transmission and reception then, because if we're going to send these signals out, they got to go somewhere, and hopefully they're going to go to a receiver that can receive them. And for that, it goes all the way back to Friis Transmission Equation, which was developed a long, long time ago in a place far, far away. Well, what I want to do is, rather than just talking to you about the formula, show you one of my favorite websites. So this is everythingrf.com. When it comes to having calculators to demonstrate these concepts, they've got them all. If we go back to our RF calculators main page, you've got dBm to watt calculators, noise factor to noise figure calculators. This has to do with components within an RF circuit system and the noise introduced by those components. Noise temperature, noise figure, wavelength to frequency, frequency to wavelength, watt to dBm. I mean, they've got it all. Antenna down tilt calculators. If you want it, they've probably got it. Some really good things here. I'm going to come down here to the RF calculators, and here's Friis Transmission Calculator. So what we need to do is enter the transmit power, and we're going to enter that in dBm. And I'm just going to keep it simple and say it's 10 dBm. And then we'll enter the antenna gain, and we'll say that it's a simple 3 dB of gain. And the receive antenna gain, we'll say simple 3 dB. And that, as you can see, is in dBi, and you can't change that. You can change the transmit power from dBm to watts if you wanted to. So that certainly is an option. And so then we come down here and we say, okay, well, what is the wavelength? Well, I want to do a 2.4 gigahertz. And so I need to calculate what is that in meters. Well, I know it's going to be 1.125, but they've got a great little link right here to their frequency to wavelength calculator. You click it and you come in here, you enter your frequency. We'll go ahead and do it in gigahertz, and we'll say 2.4. Calculate that, and you see the exact value is 0.12491,352 meters. Well, I'm going to go ahead and go with the 0.125 rounded, and that gives me then my wavelength. And then the antenna separation, how far apart are they? Because what we're going to do is we're going to use this to calculate the power received at the receiving antenna. So what we're going to do is say our separation is 1,000 meters. We'll click on calculate, and the result is you're going to lose 84 dBm. The power received will be minus 84 dBm. Okay, it's not enough to be a wattage here because of so much power lost. If I send out 10,000 or 1,000 dBm and I calculate it again, now notice I do have 3.9 watts because I'm transmitting an awful lot of power at 1,000 dBm. If I go to watts, I can put in 10,000 watts and calculate that, and you can see my power received is a little bit different there. Okay, so this is the Friis Transmission Calculator. Now you can read all about this. If you come down further, they're going to give you the actual formulas that are under the hood. This is one of the things I love about this site. It's a great learning site for studying this. And then it tells you more details about it, gives you assumptions, and it gives you the derivation of the formula. So breaking down all the parts and pieces. So you can see how to calculate even things like the antenna aperture and other parts of this particular formula. So a great website for you to know about. I encourage you, if you've never been here, take a look at everythingrf.com. You can go into their RF calculators, and you've got all of these calculators that you can utilize. Okay, so that is Friis Transmission Equation. Now, what I want to do is show you that we have a formula for calculating free space path loss specifically that is used quite often in radio frequency communications. So free space path loss is equal to 4 times pi times the distance divided by lambda to the power of 2. So the distance is in meters, the wavelength is in meters. Okay, and this gives me my free space path loss. Now this formula is going to give you a really large number, okay? And this number is not something we like to think about as wireless administrators and engineers. So what I would encourage you to do is to know that in the lower left corner, I've put it here for you, how to convert this traditional FSPL formula into dBm. All you have to do is take the results of the large FSPL formula or equation and use it in the formula 10 times log 10 of FSPL. So whatever the results of 4 times pi times d divided by lambda to the power of 2 are, take that and log 10 it and multiply it by 10. And that's going to give you your dBm value. Now, it's very important that you know that this thing I'm calling lambda is your wavelength in meters. And if you don't know it, you can calculate the wavelength, or lambda, by dividing the speed of light, c, by the frequency, 300,000, for example. Now, all of this calculation could be done in a spreadsheet if you wanted to. So here I have a spreadsheet. You will notice that I have the speed of light. I have the frequency of 2.4 gigahertz. And if we wanted to go with the center of channel 1, all we'd have to do is change this to 2412. And that's going to make adjustments to it. And you can see right here then I've calculated the wavelength, which is A1, the speed of light, divided by A2, the actual frequency. And then I have the distance. I'm going with 2,000 meters. And I use that to calculate my free space path loss, 106. Now notice that I'm looking at it in dBm here, and that's because if you look at the actual formula, and what I'm going to do is copy this and paste it into this cell here, removing the equal sign, and then we'll go ahead and widen this out a bit. So now you can see, what am I doing? 4 times pi, and I've abbreviated pi to 3.14. 4 times pi times C1, which is the distance in meters, 2,000, divided by B1, which is the wavelength, to the power of 2. So that's this inner calculation. And then I'm taking 10 times log of the result of that FSPL calculation that we saw on the slide. So that's all I'm doing in Excel in order to calculate my free space path loss. All right, let's take this a little bit further. We're going to go ahead and bring up our calculators here. And we have a free space path loss calculator right here. And we're going to plug into it. The distance is 2 kilometers, which is 2,000 meters. We could change it to meters and say 2,000. We'll go ahead and do that. So we're using the same numbers. We're going to enter the frequency in gigahertz, 2.412. And we're going to say the gain of the transmitting antenna is 0 and the receiving antenna is 0. Calculate that and look at that. 106.108, go back over to Excel, 106.105. We're slightly differing in the way this calculation is being done, but obviously all we care about is the roughly 106 dBm of loss. And so you can see that in Excel you can calculate this, and my pi is rounded more than their pi, and I'm sure that's a factor in this calculation. So we see that we can use a calculator like this. We can create our own spreadsheet. Either way, we can accomplish the same end result. Okay, that's free space path loss. Now let's wrap up our discussion by talking about what all this matters. Why do we care? Well, frequency band characteristics. Did you notice one thing was common in the Friis Transmission Equation and the free space path loss equation? They were both concerned about the frequency. When you're doing the calculators, what they're doing is using a calculation based on frequency instead of having to do the wavelength. When they're worried about the frequency and or the wavelength, and that is a factor in the equations, right? So if we go back here, the wavelength is a factor in the free space path loss equation. And you'll remember we calculated the wavelength when we did the Friis Transmission Equation. Both of them, we factor in the wavelength, which means because wavelength is the speed of light divided by the frequency, when you factor in the wavelength, you are factoring in the frequency. And there are FSPL equations that just include the frequency. Basically what we do is we take that top value, 4 pi distance, and we add frequency. So it would be basically 4 times pi times distance times frequency divided by c, the speed of light. So you can change the FSPL formula in that way and actually have frequency in it. But even without frequency literally being in it, it is in it by the fact that wavelength is in it. And so what am I saying? Well, remember, higher frequencies, shorter wavelengths. Lower frequencies, longer wavelengths. All right, well, let's see how this impacts things. We're going to switch back over to our sheet, and we're going to change our frequency. So instead of 2.4 billion, let's do 900 million. And you can see my free space path loss is now lower. I've gained roughly 9 dB, a little less, 8.6 or so dB of signal strength. Okay? Well, let's try this. Instead of 2.4 billion, let's do 5.8 billion. And now notice instead of 106, we're at about 6 dB higher, we're at 113. So you see what's happening there? I doubled my frequency, and I also doubled my free space path loss. Twice, right? So each 3 dB is a doubling. So I doubled my path loss twice, a little more than twice. If we go up to, say, for example, 60 gigahertz, then you see the free space path loss. If we go down to 400 megahertz, you can see I get, at the same exact distance, only 90 dB of loss. So clearly, frequency does impact my signal receptivity characteristics. And that is very important to understand. And this is why we've spent this time this month going a little bit under the hood. Could we go further under the hood? We sure could, and we do in the new CWICP course. This is kind of the start of talking about advanced radio frequency in the CWICP course. And we'll be going deeper as we look at more webinars later on as well. But this gets you started thinking about some of these deeper concepts. Now, what I'd like to do at this point is thank you for joining us for this month's webinar, and I'll see you next month.